So, very good morning to all of you. So, in the last class we looked at the energy bands in solids, and the energy bands which are coming out from solving the Schrodinger's equation for the entire crystal. That means, we have taken a one dimensional structure of atoms, capital N number of atoms, and then we saw, solving the Schrodinger's equation, how we can produce the discrete values for the wave vector k, and also there is another wave vector coming from the entire crystal, that is a small k, and then we saw that now this small k will lead to quasi continuous values of energy. That is one thing. The other is, when we solve the particular Schrodinger's equation, you have to satisfy the condition that you have a cos times the wave vector for the entire crystal times the lattice spacing A. So, based on this we find that there are solutions which are not allowable, and these form discrete bands where so these are basically the reason why we have the energy gaps between the different energy states or energy levels in different materials such as metals, semiconductors, insulators and so on. So, the electrons have to fill within these energy levels and also account for the discontinuities in the energy levels through these kind of jumps or band gaps. So, depending on this concept of band gap, so the band gap is inevitably going to be there. So, but the classification of these materials will now depend on the way the electrons are filling these. So, in the case of metals, the electrons will be not completely filling a particular energy level, therefore, they are free to move and this becomes the conduction band, whereas in the case of insulators the conduction band is completely filled, there is no room for the electron to move around in that energy level, and also the fact that you have a very big band gap. Okay. So, they cannot even jump from one band to the other. Okay. So, these pictures whatever I have drawn, they were all at respect to 0 Kelvin filling of electrons, that is the default state of that material at the lowest energy level possible. Now, if you are exciting this at much higher temperatures, these electrons tend to move around to the higher energy states, and for example, the picture of a intrinsic semiconductor, that means that at a finite temperature, so they can overcome the band gap or the energy required to jump from one band to the other, and therefore, they become a conducting material, whereas at 0 Kelvin they look like semiconductors, whereas at some temperature they become a conductor. Whereas, if you are looking at extrinsic semiconductors, the band gap is little too higher. So, even at normal temperatures like room temperature and above, they cannot jump across the band gap so easily, and therefore, you need an external material whose Fermi level can basically adjust either between the valence or the conduction band of this particular semiconductor material. So, the external material can be either a donor or acceptor, depending on where the Fermi level matches with this base material's conduction band. Okay. So, if it is too close to the conduction band, so we have called this as the donor. So, some electrons from the donor get excited and they get moved to the conduction band of the base material, and therefore, now the electrons are abundantly available in the conduction band to move around, then this becomes a N type semiconductor. So, whereas if you talk about acceptor material, so the Fermi level of the acceptor material will be close to the valence band, and therefore, some of the electrons from the base material jump to the acceptor material, thereby creating some empty spaces, and therefore, again in the base material you have some room for the electrons to move. So, this becomes the absence of electrons, these are called holes. Okay. There is nothing physically called holes, it is only the absence of electrons, it means just there is more room. So, this kind of semiconductor material is called the p type semiconductor material. So, from the quantum mechanical perspective, we are now able to understand why why there is an energy gap that is arising, and how as a consequence of this energy gap and depending on the filling of the electrons you can end up in classifying different materials, right. So, this is a very important step before you proceed further in analyzing the the energy transport in these materials. You have to first know their classification. So, what we will do now is just in the last class we have drawn these kind of energy bands which actually look like this, but we will only now focus on the valence and conduction bands. That is, we have seen that in all these cases, so we are mostly concerned with the movement of electrons in these two particular bands, right. So, it can be either completely filled or partly filled, or it can jump from this band to that band. So, nevertheless these two are the bands of interest. So, the lower one is the valence band, the upper one is the conduction band. In case of the p type semiconductor, even the lower one can become the conduction band, okay. But in general if you take a generic material, so we will focus only on these two bands. So, therefore, we will approximate these bands by again a parabola, right. So, essentially the lower band of this is represented with one parabola, the other one with another parabola. So, we will end up having two parabolas like this inverted, and then you have the band gap. This is your band gap. So, this is a approximation to the real energy bands. So, you can call this as energy band approximation. So, this is easier to work with if you want to do some theoretical analysis. Okay. So, why we are doing this way is that now if you draw the energy on the vertical axis, right, and now if you are talking about N or P type. So, now in the N type semiconductor, the donor will have a Fermi level which is closer to the second band, the upper band. Okay. In the case of the P type, the acceptor would have a Fermi level which is closer to the lower band. Right. So, these are the impurities, what you call the donor or acceptor. So, for the base material you are adding a certain impurity and you are doping it. Okay. So, with this case what we can do is use a Taylor series approximation, because now according to this analysis this is a symmetric one. So, that is why we can actually draw only one half, either the right or left one. Okay, we have represented only one half in the earlier figures, but actually you can, as you can see from the original graphs, they are symmetric. Okay, they can stretch from values of the crystal wave vector spanning from minus pi by a to plus pi by a, right. So, they are therefore symmetric, but you can therefore see that the movement of these electrons are mostly confined towards either the maxima of the lower band or the minima of the upper band. Okay, in most of the materials, unless they are excellent conductors or very bad insulators, where you do not have any movement at all, or excellent conductors where it may be filled all the way till here, maybe sometimes, and you have a lot of space again. But most of the semiconductor materials, for example, will have most of the movement of the electrons taking place between the maxima of the lower band and the minima of the upper band. Okay. So, therefore, we will only focus on this particular region and then apply Taylor series approximation to calculate the energy level at some wave vector, some displaced wave vector from the center at which you have the maxima or minima. first of all we do not know whether the maxima or minima is at the center, okay. It could be slightly offset from the center axis also. So, let us say that the location where you have either the maxima or minima for the wave vector is basically km, okay. And therefore, if you use the Taylor series approximation, you can calculate the energy corresponding to some vicinity of this km at some other value k, which is related to the energy at km plus what? How do you expand in the Taylor series? You have therefore derivative of this at km times k minus km plus you have half of d square E by dk square at km into k minus km square plus higher order terms. So, this is the Taylor series to the second order approximation. So, now we can therefore write this. Now, we know that at the maxima or minima point, what is the condition that we can apply? So, we have dE by dk at km will be 0. So, we are now concerned only about the region where we have maxima or minima. So, there we are using the Taylor series. So, at the point where you have the inflection point. So, this condition 0, this should be equal to 0, and therefore, so now we are making a simpler approximation to these energy bands. This is km plus half d square E by dk square Okay, now I am going to introduce another notation here. This is called as the effective mass. I use the symbol m superscript star to distinguish it from mass of a particle. Mass of a particle like electron mass, phonon mass or whatever, they are just m subscript e or whatever in the Schrodinger's equation. So, now I am using another notation m star. So, I am going to define this as modified Planck's constant square divided by d square E by dk square, this derivative evaluated at the saddle point. Okay. So, therefore, if you use this definition, you can rewrite this d square E by dk square as what? H prime square by m star. Okay. Now, therefore, we are rewriting this in the form which is little bit more familiar, the relationship between energy and wave vector that we get in Schrodinger's equation. So, now we are going to rewrite it in the similar format by, therefore, we have m star right into k minus km the whole square. So, now you see this and compare it to the energy from the Schrodinger's equation, how it is related to the wave vector. So, there how did we relate it? H prime square k square by 2m. Okay. So, now we have brought it to the similar format here, except that now instead of mass of the particle you have the effective mass m star. So, this m star is kind of representative of the crystal mass. Okay. It is not, you cannot call this as anything to do with mass of a particle here, because this is not a real mass. It is some kind of a, the units of this will come to mass, okay, but it is to do with the crystal energy bands. Okay. So, therefore, this is actually representative of the crystal mass, okay, not the physical mass, it is actually some kind of mathematical representation. So, this is basically the relationship between the energy and the wave vector k. Okay, this k is the small k, this is for the crystal wave vector. Okay. So, this is your dispersion relation for the entire crystal. Okay. So, we have therefore using this parabolic approximation, and now we have applied the Taylor series and we have come to this. We can use it for different materials, and we can actually rewrite this in terms of conduct. For example, if you are applying this to the conduction band. Okay. So, the corresponding energy will be equal to the point where you have the minima for the conduction band. So, this is your starting of the conduction band, correct. So, that is this point. So, this point is the starting of your conduction band, this is the point where your valence band ends. Okay. So, therefore, if you are applying this to the conduction band, where suppose you are talking about metals, so your conduction band is partly filled. Okay. So, in that case the starting point will be the minima of the conduction band, plus you have half h bar square by m star, and now you can also assume that it is symmetric about the center line. So, the point where you have the minima is k m equal to 0. Okay. So, therefore, this becomes much easier to approximate. So, for example, you can talk about metals. So, this is a dispersion relation between the energy and wave vector. Okay. So, therefore, if you are just to summarize the transition from the simple systems in quantum mechanics to a real structure. So, in the case of quantum mechanics of simple systems, so that is, let us say, quantum well. Okay. So, you have basically the 1D quantum well. So, in which how was the dispersion, or how was the structure of the energy levels. So, you had a quantum well like this, and then you had a width of say capital D, and on the vertical axis you have the energy. Okay. So, this cannot escape the potential energy constraint outside say u equal to infinity. So, in this case you had different modes. So, your energy levels were all quantized. So, defined by the jump in the wave number or wave vector. So, k equal to n pi by d. Okay. So, you have n equal to 1, you have a particular wave function and corresponding value of energy, and for n equal to 2 you had a particular wave number corresponding value of energy, and n equal to 3 n equal to 2 n equal to 2 and n equal to 3 and so on. Okay. So, therefore, so you had your discretization of the wave number where n equal to 1, 2 and so on. So, correspondingly your energy levels were also discontinuous and they were quantized. Now, in the case of a crystal structure, when you are looking at the quantization, now two levels of quantization are there. One, your k is quantized in the crystal. How is this related? 2 n pi by L. You have seen this, okay, in the case of crystals where n can take the values plus or minus 1, plus or minus 2 and so on. Okay. So, this is one level of quantization, the other is due to the solution of the Schrodinger's equation and the solution which says that there are non allowable solutions and therefore, there are band gaps. So, the consequence of applying the quantum mechanics to a crystal now is on top of these discreteness in the wave vector space, also you have jumps between the energy levels resulting in the band gaps. So, therefore, you ended up with you had a particular band. So, in fact, these were all discrete. This is what I meant by you are plotting this with, for example, k a by pi. So, I want this concept to be very clear, so that you do not get confused. So, this discreteness here in small k results in this quasi continuous bands here. These are not perfectly continuous, you are just discrete, but we are representing it like this. Now, these are equivalent to these jumps. Okay. On top of this, you also have gaps between the energy levels. Okay. So, therefore, the next energy level would be looking like this, and then you have the next energy level like this, you have the next energy level like this. Okay. So, in the crystal structure, therefore, you have one level of discontinuity because of this k, and also the other level of discontinuity due to this band gaps. Okay. So, this is your real dispersion curve, and then we made an approximation to these bands, these two bands for example, and then we have arrived at this particular dispersion relation here. Is it clear? So, what we will do next is, now so far we focused on the electrons. So, the electrons confined by a certain potential energy constraint due to the interaction of atoms in a crystal. So, we will now move on to what will happen to the vibrational energy of these atoms. Okay. So, in actual crystal, now we also looked at the simple harmonic motion for a single atom. Okay, we looked at spring mass system equivalent, and then we derived the quantum mechanical energy states h nu into n plus half, right. So, n can go from 0 all the way. So, now if you expand this to a crystal with n number of atoms, so how is this interaction between atoms going to be accounted in this harmonic motion? So, this will be the next. So, basically you have the vibration of atoms, vibrational energy of atoms in a crystal. So, we are going from quantum mechanics of simple system to now more complex systems. So, we did this for electrons, now next we will do this for phonons. Okay, that means these are what? Phonon waves, right. So, once again we have analyzed a single particle vibration, vibrational energy state before. So, now we will do this collectively for many number of atoms together. So, these will be the actual vibrational waves which are termed as fictitious particles called phonons. So, therefore, we will construct a simple model for analysis. See, there are many ways of looking at this. You can actually solve the Schrodinger's equation again, but we will now resort to a more common and simpler way of handling this collective vibrational energy of the atoms. So, unlike the electron case where we were more rigorous, we knew the potential energy constraint and solve the Schrodinger's equation. Here we will use some classical mechanics, okay, some kind of conversion to the wave nature, and then we will bring in whatever we have already derived in the quantum mechanics for a vibrational energy and plug it into this. So, we are going to do some little bit of ad hoc approach here, but that is probably the easier way to deal this problem. So, you can imagine the interaction between all these atoms together as several masses connected by springs. Okay. So, you have therefore, one atom described by this particular mass, neighboring atom, and the interaction between them through a spring constant. Okay. So, we will consider only a simple harmonic motion like this back and forth. Okay. So, like this you have several of these atoms in a crystal. So, all connected by the same spring with the same spring constant, and the separation between them can be denoted as A. So, you have n number of atoms forming a crystal. So, this is just a one dimensional representation. So, we are talking about 1D representation. The actual crystal is 3 dimensional. So, we will also have in the vertical direction into the depth, but we will decouple all of them. We will not say this motion is going to influence the vertical motion. So, we will have decoupled things, and later on we can linearly superpose those solutions. So, first we will therefore look at only the 1D representation. So, the total length of this 1D chain of atoms. So, these are basically monoatomic crystal. You understand? So, you have basically only one kind of atom in the crystal, and they are all just equidistant spaced and they are separated. You can also have a polyatomic structure. You can have 2 atoms, one bigger size, one smaller size, with different masses. Okay. But right now, to start with, we will look at the simpler system. The total length of this chain therefore will be n times A, where n is the number of atoms. So, the particular coordinate of an atom. So, here for example, this atom we will call this as j times A, where j is an index. Okay. For example, if this is the 4th atom from the left, so this will be number 4, okay, and therefore, this will be j plus 1 times A, and this will be j minus 1 times A. So, these are the actual coordinates. Okay, I am using this index notation here because you can apply this to any of these atoms.
So, the length will be n A or n minus 1?
Yeah, this will be a collection of so many number of atoms that practically it will not make a difference if you use n or n plus 1. So, if you are talking about 10 power 26, 10 power 28 number of atoms, so it will not make any difference if you add 1 to that. Okay. So, we can just make it as Na. Okay. So, therefore, what we will do now is go back to classical mechanics. So, this is where we will do some little bit of cheating. We will not follow the rigor that we did for electrons. We will just use the Newtonian mechanics here, F is equal to ma. So, that means we will consider a particular atom here at location J and look about the forces acting on this particular atom. So, you have one force acting in this way, the other force which is acting in this way. So, there is a pull coming from here, pull coming from here. Okay. So, therefore, the effective force will be the difference between these two forces. Now, can you write down what will be the force acting on this direction? That means between, let us only consider neighbors now, let us not complicate it by including a very large neighborhood, just immediate neighbor. So, that is the force between this atom and this atom. So, we know the spring constant K. So, I want you to just write down the forces. Now, let us also, I will give you some nomenclature here. Let us say that the equilibrium position of this atom to begin with is x j superscript 0, this is your equilibrium position of atom J A. Okay, at location J A. So, now if you are pulling now from this equilibrium position, okay, there is a certain displacement. Okay, so, therefore, the actual displacement from this equilibrium position will be, let us say we will use this notation u j. This is not velocity here, this is your effective displacement from the equilibrium. So, your new location would be something like x j minus your original location x j, right. So, this u j is actually the effective displacement from the equilibrium position. So, therefore, knowing the displacement of this atom j, and similarly you will know the displacement of the atom j plus 1. So, you can calculate the force which is acting this direction first between the atom j and j plus 1. So, can you express this? You also know the spring constant, and then similarly write it for the other force. So, what will be the force? How can we write it? Spring constant times u j plus 1 minus u j. So, u is the effective displacement from the equilibrium. So, we will use u not x, right. So, similarly, yeah, you are right. So, this is equivalent to x j plus 1 minus x j, but we will write in terms of u. Similarly, in case of F2, k times u j minus u j minus 1. So, therefore, the net force will be the difference between this and this, right. So, the net force which is acting in this direction, which is pulling the particular atom j to the right, will be this force minus this. Now, what will happen in the wave nature? Now, this will produce a right running wave effectively in this direction, right. So, therefore, the net force will be k times u j plus 1 minus u j minus, so you have 2 u j plus u j minus 1. Okay. So, this is the net force acting in this direction. In terms of wave picture, it will now produce a right running wave which is moving in this direction, this vibrational energy. So, therefore, now going back to the classical mechanics, m into d square, what should I write here? U j by dt square. This is the acceleration of this particular atom in the right direction. This is equal to k times u j plus 1. So, I can multiply and divide it by a square, where a is the lattice spacing between the atoms. So, therefore, now what do I see here? Anybody who has done numerical methods? So, this is the central difference form of what? What is the operator? d square uj by dx square. This is the numerical approximation. Now, because we are working with discrete spaces, because a lattice is what? What is a crystal? Crystal is nothing but atoms which are located in discrete points in space. So, what we can get here is only a discrete representation. If you want to transform this into a continuous derivative, so you have to imagine like you apply a numerical approximation to a continuous derivative and then you back transform that. Okay. So, therefore, if you want to write this in terms of a continuous equation, so therefore, you have m d square uj by dt square will be equal to k square into d square uj by dx square. So, what kind of equation is this?
Why it is a and
Huh?
Why it is down since it is a single dimension with the right hand side.
Correct, but now we are writing this in terms of space. So, to distinguish this, so we will have uj which is now function of both space and time. So, therefore, we have converted that into partial differential. So, what type of equation is this? Classical, mathematical, parabolic, elliptic or hyperbolic? Why elliptic? How many of you say hyperbolic? So, this is basically hyperbolic equation. This is your wave equation. People who have done some differential equations, you must have studied. This is your wave equation, and wave equation is always hyperbolic. This d square u by dt square will make all the difference. If it was just du by dt, this would have been parabolic equation. Okay. So, this is your hyperbolic wave equation. This is your also called your telegraph equation, whatever. These are basically all these are waves. So, to describe the waves, so this is your commonly used wave equation. Okay. So, you have displacement of a string that you study in your partial differential equation, that is basically governed by this equation. From some equilibrium position you displace the string and you have waves. Now, you want to study how these waves are propagating from the initial condition. So, you solve this PDE for that. Anyway, so coming back to this problem, therefore, what we have is we are trying to find a solution to a discrete problem. We are trying to find a continuous solution to a discrete problem. So, we are discretized already points in space, and now we have transformed this into a continuous equation here. So, how will the discontinuity be addressed in this continuous solution? So, we will see that. So, now what it means, you have a wave, therefore, which is propagating, but in which direction it is propagating? Effectively towards the right. So, the solution to this will be a right running wave. Okay. So, which will be a e power minus I omega t minus k x. So, this is your solution to this equation, right. Now, this is a continuous solution, but we have a discrete set of points. So, therefore, how do we transform this? We just plug in for x as what? X is continuous. So, now we will use j times a. So, therefore, for this particular problem you have a e power minus I omega t minus k j a. So, now this becomes a discrete solution. At each and every location j you will find the corresponding. So, what you can do is substitute this solution into, let us say this is equation 1 and this is your assumed solution for the wave equation. Substitute this 2 into 1, this should eventually satisfy this, and you write down the relation between, now omega, what we have is your angular frequency here, right. So, this omega, and we want to construct a relationship between k, this k here. Okay. Now, let me not put this into, yeah. So, this is your k, we are using only one k here, or we are no. So, this is now this k is your spring constant. Okay. So, I think let us use kappa here, this kappa is your wave vector. What is that?
S is in suffix, because kappa and k is not much different sometimes that because of lighting, and S is suffix.
Yeah, okay. So, you use I mean whatever notation you want, but this is your spring constant here, and this will be your wave vector kappa, you can denote it like this. So, you substitute this into this equation, write down the, therefore, a relationship between omega, okay, this is also your kappa. So, write down a relationship between the frequency, angular frequency omega and kappa. So, this is, what is this relation called? Dispersion relation. So, in the case of electrons, you used energy E versus the wave vector. So, in the case of phonons, the energy is now denoted by the angular frequency omega. How it is related? H bar omega. Okay. So, therefore, now we are having a dispersion relation for phonons between omega and kappa. So, can you do that? I will give you 5 minutes time. I think you should be able to do this. K A square.
Small a.
This is your final relation you are getting? First find du by dt, then you find d square u by dt square, okay, and then you substitute. First find out du by dt. So, what do you get? Du by dt. So, A E I, so you will have, yeah, A E I K. So, let me separate the spatial part out. Okay. So, then you have E minus I omega t into minus I omega, right. So, then you do d square u by dt square. So, now this is again a constant, you will not, and now this will be again e power minus I omega t. So, this will be minus I omega the whole square. Okay. So, now the time derivative is determined. So, similarly find out the spatial derivative.
So, m omega square is equal to k into the first one.
No, It is not that simple. You will have a trigonometric function there. Should have a sine function on the right hand side in terms of kappa. So, what you can do now is you can substitute this 2, in fact, to make it easier you can substitute, let me call this as equation 1a. You can directly, because this is a discrete one and this is also a discrete solution 2. So, directly this 2 can be substituted into 1a. Okay. So, then the right hand side part becomes discrete. So, you do not have to worry about it. So, therefore, substitute 2 into 1a, I should say. Okay. So, substitute 2 into 1a, which is the discrete equation. So, you have, I will just write down m a e power I, this is the temporal part, minus I omega square e power minus I omega t. So, now the right hand side is already discrete, you just plug in for the appropriate index I omega t minus k, what do you have, j plus 1a, right. This is u of j plus 1 minus 2 times u of j. So, this is a e power minus I omega t minus k j a plus you have u of j plus 1, you have u of j minus 1 e power minus I omega t minus k j minus 1a. So, now if you cancel all the common terms, you will be getting minus omega square m is equal to k and e power I, this is your kappa, plus e power minus I kappa a minus 2. Okay, so, you can actually pull e power minus I omega t out and cancel off left and right, because they are common, and this is what you will get. Now, you use the relationship between this and your trigonometric functions. Okay. So, tomorrow you tell me how will you convert this into a trigonometric function, therefore, from that what will be the relationship between omega and kappa. Please do this as a homework, from there we will continue. I do not think you might remember the relationship between this directly and the trigonometric functions. So, what will this be? Okay, 2 times. Okay. So, we have cos k a minus, so we have 2 common, so this will be minus 1. So, therefore, how can we write this again? 1 minus cos k a minus 1. So, this should come out to be sine square, yeah, we can use the half angle formula, half angle trigonometric identity, kappa a by 2. So, therefore, your omega can be written as 2 times square root of, so omega can be positive only because it is like energy, so it cannot take negative values. So, this is your spring constant here, and you have absolute value of sine kappa a by 2. This turns out to be the dispersion relation. Where?
1 minus cos theta is 2 times square theta.
Yeah, this is a half angle formula. This is not simply 1 minus cos square is equal to sin square theta. So, this we are using a half angle formula, you please check that. Okay. So, yeah, now the thing is all this we have derived by classical mechanics. So, now how are we going to apply quantum mechanics to this? Now, remember our energy levels for vibration. So, we have derived E n is h nu n plus half, right, or we can write this as h bar omega, h by 2 pi into 2 pi, h by 2 pi is h bar times omega. Now, there we had relationship of nu as 1 by 2 pi square root of k by m in the spring mass system, okay, in the simple harmonic oscillation. So, now this omega is now become what? Discrete, 2 times square root of k by m. So, similar, but you have absolute value of sine kappa a by 2. Now, your kappa is what? 2 pi n by L, where n is plus or minus 1 plus or minus 2. Now, this has become discrete and therefore, your omega has become now discrete, you understand. So, now this is how for the actual crystal your energy levels have become discrete. So, again you have two levels of discreteness, one is your n here, maybe you can use m here to distinguish that n and m. So, your n here is one level of quantization, okay, which is taking values from 0, 1, 2 and so on. The other discreteness is in your value of angular frequency omega, which is now a function of the wave vector, which is again now discrete. So, just like your electron energy levels, now you have again discreteness not only in the modes, okay, but also in the energy levels, energy bands. Okay. So, this is how we are now dealing with the phonon energy level. So, we have really not solved the Schrodinger's equation fully, we have assumed the same energy, vibrational energy levels or energy whatever we have derived before should hold true for this system, except for the fact that now omega is now modified through this dispersion relation. So, we will stop here and tomorrow we will continue what is the consequence of this. Okay? Thank you.